Yes, sir.
So we'll start very quickly. So first thing is the chapter 1. Chapter 1, which is a kind of background, or we can write it as a quick recapitulation. Okay, so there are many things we need to recapitulate, mainly probability statistics we need to recapitulate. So we'll start with the probability. So section, I will write like this, chapter section, so that it will be more structured. Section 1.1, it is probability. Okay, quickly I am trying to proceed. So there are few definitions, we should write it quickly before going to probability, axioms of probability. First is experiment, all of you know it, so I'm going very quickly. So it is a procedure we perform. So experiment means always you feel that something in real world need to do. It is not necessary. It is quite maybe hypothetical and thought experiment, that is also fine. Okay, a procedure what we perform and receive some results. So if you think that what experiment is, that means some procedure and some result. So if we give some example, suppose tossing a coin, that is definitely an experiment. So you see there are two things: procedure, that means we toss the coin, and result, what you obtain. And something is hidden which we don't explicitly tell here, but say we assume many cases the coins are unbiased, both the sides are equally probable, that will come. So those assumptions are also inside the experiment, which we generally don't explicitly tell, but that is. So part of the experiment is the procedure, outcome, and the assumptions. Now what is outcome? Is a result, possible results of experiment. Outcome is possible result. Then what is event? Event means a certain set of outcome that we call as event, right? So when we do experiment, that means some procedure and the outcome. So we generally define experiment with the letter E. When you say the outcome, generally we define with the letter Xi. When you say what is the event, generally we define that with the C, or sometimes we define it with A or B or whatever, like this. Now the last thing what we remain, the sample space. Sample space means, so it's a collection of set of all collection of collection or set of all possible distinct, that means collectively exhaustive and mutually exclusive. What does it mean? Can you explain, anybody? So collection of set of all possible distinct outcome of experiment. Okay, so we generally call it S. is a standard. This is the sample space. Okay, so now these are the few quick definitions. Now can anybody explain what do you mean by the collectively exhaustive and mutually exclusive? Can anybody give some explanation? Mridul?
Yes, so the outcomes at a at a specific time, one outcome can only be possible. It's is meant by mutually exclusive, and collectively exhaustive means it is all the possible outcomes which are possible for any experiment.
No, collectively exhaustive means if you take all the events, you will get the full universal set. Okay, that means you collect all the events, it will become exhaustive. That means you will get the full universal set. And mutually exclusive means if you take two events, they are mutually exclusive. Okay, there is no intersection. Okay, so these are the three things, few things. So now let's give some example. Can anybody speak and give example? Suppose I am giving an experiment is a rolling of a die. Okay, so a cubic die we are rolling. So this is the experiment. Now can you tell what may be the outcome and what may be the event and what may be the sample space? Anybody? Maybe Jafar?
Yes, sir. So
Yes.
the outcomes can be any number of the die, like
Yes.
be it 2, 3, 4, 5, 6.
Right.
So, and events, we can form any set. Like let's assume that the number we are getting is less than 4, and there will be we can form a set,
Right.
and that can form an event. And for sample space, we can take like numbers that are less than 6. So that will
Like
give us
no,
samples.
no. Sample
No,
space
no,
will always be 6.
one.
Sample space is the all 1, 2, 3, 4
Yeah,
all.
all the events. Sorry.
And you see that those are mutually exhaustive, mutually exclusive, collectively
Mhm.
exhaustive. If you take two things, there is nothing remaining. If you take two things, suppose one or two, they are mutually exclusive. Okay. If one comes, two cannot. So that is the thing. Okay. Let's proceed quickly. I don't want to spend much time on it. It's for the sake of completeness only. And then the axioms of probability, all of us know. Axiom of probability. So what do you mean by the axiom? Anybody? Quickly. Satipriya, what do you mean by the axiom?
Set some assumptions for probability.
Actually, axiom implies that if we give some statement and say that this is axioms, that means these statements are taken as the self-evident and we don't need proof or we cannot prove. Okay, so axioms we cannot prove or we don't need proof. So that is the kind of statement which says that it is self-evident or our convention or our assumption. Okay, so axioms cannot be proved. So that is what it is, a fundamental thing of the statistics. So for any event A, there are three axioms of probability. For any event 3, any event say A, that's what I was saying, it called a PR I call as the probability. PR of A will always be greater than 0, so it is a non-negative number. And if the sample space S is a sample space, so S is a sample space, that's what I say, sample space. So PR of S will be equals to 1, and if there is no intersection, that means A union B, sorry, A intersection B is a null set, then probability of A intersection B will be equals to probability of A plus probability of B. Okay, so you see that whatever we are saying that for any event A, probability of A is greater
Sorry,
than
sir.
0. Yes, please.
The number third, probability of A intersection B or probability of A union B?
Sorry, A union. Okay. So if you see that the probability is always in between 0 and 1, and last three, number 3 is always is okay, fine. So now see that we are defining the probability cannot be negative number. It will be always positive and it cannot be more than 1, because S is a sample space and it is all the probability in the all the event in the sample space. If you consider, it will be 1. Now if you have any question that whether can we define the axioms differently, say probability of A will be greater than 0 or less than 0, anything, and sample space can be -100 to +100, like that, definitely we can define. But then our, if anybody define like that, that is not the convention, so that is not acceptable. We need to follow the convention. But those who have defined it earlier, they can easily define it in a different way. But as we defined and we are following the convention, we have to follow that probability will be always in between 0 to 1. Okay, is that clear? Any query? So this is clear assumption and we have to follow this. Any query up to this point? Okay, so then quickly some theorem I will state, which is very obvious to prove. So just one line proof. Theorem is probability of A bar will be equals to 1 minus probability of A. It's very simple theorem. It can be proved very quickly. Just if we take probability of S equals to 1 and S will be equals to A union A bar, and then it will come very simple thing. So probability of S will be equals to 1 will be equals to probability of A union A bar. So will be equals to probability of A plus probability of A bar. So probability of A bar will be 1 minus probability of A. Okay, it's very simple. So let's move quickly. Now few more things will be coming, which is becoming more and more important. So the first thing we'll say, so now up to this point, is there any query? Please ask. Anybody wants to ask anything? Okay, so now if you say that how we will determine the probability, definitely we need to see that what is the sample space and what is the event, and then if we take the probability of sample space of 1, and then what will be the event and how much probability is, so that we can quickly calculate the probability. There is another approach which is experimental approach, which is generally people don't discuss it. Suppose you want to calculate the probability of getting head if you toss an unbiased coin. So then what we could do, definitely we can think that if we toss an unbiased coin, we can get head or tail. So our sample space consists of 2 elements, and then getting head, as it is equally probable, so it will be 1 by 2. Now the another thing you could do experiment. Okay, so just you can flip the coin again and again and again, and suppose if you flip a coin 10 times, you might get 8 times head or 2 times tail. But if your number goes to infinity, say 10,000 or 1 lakhs, then gradually you will see that you are getting the probability total number divided by the number of head is coming closer to 0.5. So that is called the relative frequency approach. So by that means also you can calculate the probability. So we can write it that probability of A, so relative frequency approach, so in this approach you could write probability of A will be equals to limit n tends to infinity, number of A getting, and then total number of trial. Okay, in that way you could proceed. Okay, now there are two things we should tell. So this is the probability, we can call that 1.1.1 as the basic of probability, basic concept. Then we can move to next 1.1.2, which you can call next subsection. So this is also very important. What is joint and conditional probability? It is very important. So what is joint probability and what is conditional probability? This is very important. Can anybody say what is joint probability? Anybody have any idea? Quickly you can say. There is no harm if you are not correct.
Sir, probability of happening two things one after other, joint probability.
No, that is not joint probability. One thing can happen one after another. Asna, can you tell anything?
Sir, probability of two events like when they happen at the same time,
Yes. That is called
joint probability.
joint probability. Okay. So suppose we have two events. We have two events A and B, right? Now, what will be, suppose we are interested that calculating the probability of happening two events A and B, right? So that means that the probability of happening two events means probability of happening A as well as B. That means A intersection B, right? So that is called the joint probability. Am I correct? Am I correct or wrong? Asna?
No, sir. Sir, it's like their probability should be multiplied. Like if we have two events A and B, then the joint
That will
probability.
come. That will come. That is the inference. That is not the definition. So joint probability means two events should happen simultaneously. Okay. The probability is referred as the joint probability of A and B when A and B are both intersection. That means both happen, and then so usually what you used to say, we note it as a probability of A comma B. Okay. Now suppose the joint probability of set joint probability of set A1 A2 dot AN will be is the probability of A1 intersection A2 intersection A3 dot intersection AN. Okay, and that we simply write by probability of A1 comma A2 dot comma AN. Jafar, is that correct?
Yes, sir.
Yes, the calculation is different. What Goel Asna is saying, that is the calculation that will come, but the definition is like that. Joint means both will happen together simultaneously. Okay, that is means the intersection. Okay, so now the thing is that suppose it A and B are two events which are mutually A and B are two events which are mutually mutually exclusive. Okay, so then what will be the probability of A intersection B or probability of A comma B? Tell me what it will be. It
0.
will be 0. Probability of phi null set will be equals to 0. So this is the very simple concept of joint probability. Now the conditional probability. Okay. Okay, what is the conditional probability? That means, so from the probability we see, it may happens that say something happened, then what is the probability of getting some other event? That means what is the probability of event A when there is a condition that B has already happened? Okay, so we can say that that occurrence of one event may depend on the occurrence of another, right? Sometimes when we toss a coin, there might not be this dependency. It head may come or tail may come. Whether earlier case head has come or not, that have no dependency. But suppose when we are drawing a card, so we have a 52 number of cards in a box, and suppose we are drawing a card, and we say that what is the event or probability of getting a heart of 1 or something. So that is something, so there is no condition. Now if I say that what will be the probability of getting this, provided that we have already drawn a black card or something like that. So for example, we can say that the event A, which is defined as a red card is selected, what will be the event A? Suppose I have a packet of cards and the event A, I am saying the red card is selected. So the probability is half, because we know half of the card is red and half of the card is black, right? Now, if it is known that the event, another event, a heart is selected has already occurred, then what will be the probability that A of the event A, which is a red card? Tell me, what will be the probability?
1.
1, because it's red only, right? So now you see, now you see the difference. So first thing what I'm saying, which is not conditional probability, just simple, I'm saying that the event A is a red card selected. Event A is a red card selected. So what is the probability? Definitely probability of event A will be equals to half, because in 52 number of cards we have half red and half black. So now then I am saying that another event, I know the event is C, which is a heart is selected. Now I am saying that what will be the probability of getting a condition that the event C has already occurred. That means the heart is selected, then what is the probability? So then the probability will come as unity, because it is already red. Is that clear to everybody? Okay. So how we will write this conditional probability? So we would write the conditional probability as the, in short notation we write P, we write PR A/C. That means the probability of event A when C has occurred. The probability of event A when C has already occurred. So A/C. So this is the conditional probability. PR of A means only probability of A. When you say PR of A/C, that means the probability, conditional probability of A, provided C has already occurred. Okay. Or sometimes in short, when we say that probability, we call it probability of A given C. That means probability of A when the event C has already occurred. So now, so we have some definition, that what is the definition of, this is the concept, how the conditional probability is coming into picture. Now the definition of conditional probability, could say that for two events A and B, the probability of A conditioned on knowing that the event B has already occurred, that is PR of A/B, which is nothing but PR of A, B by PR of B. PR of A, B means that is the joint probability of A and B. Yes, intersection, and by short we write by comma, and PR of B is the probability of event happening B. So now you see that this is the definition, and you should be able to verify the concept from the definition and conditional probability. Now if you think little bit, you will definitely could verify that. For example, when we say that some condition probability of A when condition B, that means what? That probability, then what is your total sample space? Your sample space become very squeezed. It becomes B because already the event B has occurred. And then what is your probability you want to calculate? That is P A intersection B. So conceptually you can think this is the definition, but conceptually also it is very correct, and you can already verify it. Suppose this is A. Just 1 minute. Suppose this is your sample space S, and say this is your A, and say this is your B. Now what I am saying, that B has already occurred. That means this portion has already occurred, and then A is occurring. That means what is your sample space? Your total, now your modified sample space becomes B, and then what is your event? Event will become A intersection B. So the probability will become P of intersection B divided by P of B. So that is what the definition is. It correct? Okay. Now tell me, anybody has any or you need clarification quickly, because I am trying to go through it very quickly without going through any example or anything, so that we could enter our main area very quickly. So this is kind of brush up, so all of us know these are the concept, very basic concept. So tell me if you have doubt in it. So these things will be very useful, and this joint probability and conditional probability will tell till the last day of our class. Okay, so we'll play with these two things, conditional probability and joint probability, till the last of our class. That's what I want to say, that everybody should clarify these two concepts. Okay, shall I proceed? Everything is fine to all of you? Okay. So now then comes a very important concept, which also will play the role till the last class of this course. That is called Bayes theorem. Proof is very simple, but the implication is huge. Okay, so Bayes theorem, it will play a huge role in any statistical inference. So what it says? So the theorem says, for any event A and B, and we definitely assume that B is finite, that means probability of B is not 0. For any event, this one generally people don't write, anyway we need to see, otherwise by 0 we cannot divide, that is the reason. For any event A and B, we could write probability of A given B will be equals to probability of B given A into probability of A by probability of B. Okay, this is called the Bayes theorem. So if we have probability of A condition B or A given B, that will be same as probability of B given A into probability of A by probability of B. So why it is so much useful? Let's prove it first. Proof is very simple. Just one line proof. So probability of A intersection B or A comma B, joint probability, will be equals to probability of A slash B into probability of B, which is equals to probability of B slash A. Okay, from the definition I am writing, you see the definition, whatever this one, from this one I am writing. Okay, so probability of B slash A into probability of A probability of A. Now if you see, if you take these two, quickly you could write probability of A slash B will be equals to probability of B slash A into probability of A divided by probability of B. Very simple. Now can anybody explain why Bayes' theorem is so powerful and so useful? Anybody? Okay, you see that probability of A given B and probability of B given A is not same, right? So now from here you see, if you know the probability of A given B, you can calculate B given A or vice versa. So now if you want to go for the inference, something you know and you want to calculate the other things, or on the next stage you want to predict, okay? So those things can be dealt with this Bayes theorem. Okay, that is what the theorem is very useful. Now this theorem has some extensions. So if we have, instead of one B, if we have many B's, okay, that means B1, B2 like this, and then how the theorem will look like. That is also very simple. Let's write this here. It's not very difficult. So suppose we have a sample space like this, which is S, and we have a set like this, say this is A, and then say we have a various subset kind of thing, which is, say this is B1, this is B2, this is B3, okay, this is B4, this is B5, or something like this. Now from there, if you see that we could easily write, so B1, B2, B3, B4, B5 dot dot Bn are the set of B1, B2 dot 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 Bn are the set of mutually they are mutually exclusive event. There is no intersection. That's what mutually exclusive. And also exhaustive. Why exhaustive? Because if we consider exhaustive, if we consider all B's, you will get a set of S. Okay. And if we consider Bi intersection Bj, you will get phi for I not equals to j. So if you see, union of I equals to 1 to n Bi will be equals to 1, and that will be equals to summation of probability of Bi I equals to 1 to n. Very simple. If we take all the probability, sum it, you will get 1, and that is due to these are the mutually exclusive and exhaustive events. So now if we want to calculate probability of A, how we can calculate probability of A? How we can calculate? So we know the probability of A. Suppose we consider B1. B1 has intersection. So if we want to consider probability of this much, that means we can consider probability of A slash B into probability of B. So this we can write, probability of A will be equals to summation of I1 to n probability of A slash Bi into probability of Bi. So that is the other way. So this is the theorem. Proof is also very simple. You can go with it. So probability of A if we want, so probability of A given B1 into probability of B1 plus probability of A given B2 into B2, like this. You keep on going. This is kind of, I should draw it properly because there is no intersection here. It should be like this, all the intersections. Okay, fine. So this is the case. So this is the kind of extension of Bayes theorem, or we call the theorem of total probability. Now if we know this is nothing related to Bayes theorem. This is the theorem of total probability. So with the help of this theorem, we can prove the Bayes theorem, which is little bit more complicated with those number of b. So this is also Bayes theorem, which generally used very frequently. So this will be, so if b1 b2 dot bn be a set of mutually exclusive and exhaustive event, then probability of bi given a will be equals to probability of a given bi into probability of bi by summation I1 to n probability of a slash b I into probability of bi. Is it correct? So everybody agrees? Tell me, what do you think? So the denominator you see right hand side, that is a kind of normalizing factor, and it needs to be normalized with the probability of a given b into probability of bi. So if you see this below one, if you do it, you will get probability of a. You see the probability of a will be equals to this, and if we substitute that in the Bayes theorem, you will get this. So you see that this one is coming from here, okay, and bi slash a is a slash bi into bi divided by probability of a, which is nothing but this when you have a b, all the b's which are mutually exclusive but collectively exhaustive. Okay, I spoke lot of things. Now tell me your opinion, your comments, all those things. I want you to speak. One by one, everybody.